Township.
Okay, hi everybody. Welcome to our last official foundations talk for the semester. Today we're going to have Sanne Vergouwen. Sanne is a student, a PhD student at Utrecht University, and has been working with Niels Martens. Sanne will be around all month, so if you would like to meet, feel free to set up a meeting anytime. I also want to say that our next unofficial, like not part of the main series foundations talk, will be May 19th, where we'll have Don Pesci talking. So that's the week of the annual meeting. So keep an eye out for an email about that. Okay, great. So Sanne's going to be talking to us about black holes as massive spacetime.
Yes, thank you very much. Thank you for having me. Very happy to be here. So I'm going to talk today about joint work with Niels Martens. And we are part of the Cosmo Master Group. And the main aim of this group is to critically reflect on the distinction between space-time and matter. And in this presentation, I will do that in the context of black holes. And I'll specifically look at what the mass of black holes can tell us about this distinction. So first, I'll say a little bit more about this dichotomy between space-time and matter. Then I'll present 6 tentative ways of interpreting the mass of a Schwarzschild spacetime. Then I'll focus on one of them in particular, the global interpretation, and present a particular definition of the global interpretation. And I'll end my presentation with seeing how these different interpretations, what they claim on the position of supersubstantialism, which I'll explain a little later, and come back to the distinction between space-time and matter. So this dichotomy, I think traditionally we are very much used to thinking about these as 2 different things. And in a paper from 2020 by Niels Martens and Dennis Leenkel, they challenged the tenability of this conceptual distinction between space-time and matter in the context of dark matter. And in that paper, they gave a list of criteria of what counts as space-time and what counts as matter. And I will also use these criteria in my presentation. So for space-time, they found that often people consider space-time to be a differential manifold with a connection or Lorentzian metric or causal structure, such that Watts and flux behave locally, such as in special relativity, and light rays and test particles move on the geodesics of the metric or connection. And for matter, we usually think about matter as something dynamical and something that interacts. There's actual reaction there. Also as something that possesses an energy, or that possesses a rest mass, which is kind of a strict criteria, but it's also something that's that we really are very much used to thinking about matter to have. It's kind of seen as a decisive criterion. So like I said, I will look at this dichotomy in the context of Schwarzschild black holes and ask the question, what do they teach us about this distinction? And I will approach this question by focusing on the last 2 criteria that I mentioned for matter, namely energy and mass. In the paper, they give these 3 sub-criteria for energy, but I will also use them for mass, namely being represented by a stress energy tensor, being ascribable to each point in space-time, and being ascribable to a particular space-time volume. So now, having identified mass and energy as key features of matter, let us turn to the mass of a Schwarzschild spacetime. So a Schwarzschild spacetime is an exact solution of the Einstein field equations in general relativity. It's taken to be describing a black hole. It's static, strictly symmetric vacuum spacetime, and this is its metric. So what the next few slides will focus on is on this parameter and understanding what it is and how it is justified to be a mass. So we have come up with several ways of approaching this question, several ways of interpreting the mass of a Schwarzschild spacetime, which are all summarized here, and the credits for this nice slide goes to Niels. And we think that all of these different interpretations capture some essential aspects of the mass of a Schwarzschild spacetime. So I'll quickly go through them. The first one, a dimensional analysis, it's a very thin interpretation. It only says, well, this M parameter, it's a mass because it has the right dimensions. Then the second one is the Newtonian trickle down. And this says that in a weak field regime of the Schwarzschild metric, the behavior of the test particle is approximated by the behavior of the test body in a Newtonian gravitational field sourced by mass with that same numerical value m. And the special relativity idealization, this is based on the idea that you can kind of understand the Schwarzschild black hole as a point particle, can replace it by a point particle, and then its mass is described by the length of the forward vector that you ascribe to it. And as a genesis interpretation, this justifies interpreting this parameter as m, because it's based on the idea that if you throw a lot of heavy things at a spot, then that's what could create a black hole. Then the singularity interpretation, that's the idea that at the singularity, it's there's like hidden matter. So it's kind of the singularity is a placeholder for other matter, which is massive. And then the last one is the global interpretation. And I will discuss this one in a bit more detail. This one, I think, is particularly interesting because it's formulated within general relativity. But also within general relativity, this quote, I think, is particularly applicable. I found this in a paper from Wendy Paget from the 1990s, and she talks about mass definitions in general and how there's not much agreement about them among physicists. But particularly in general relativity, I think this holds up very well. There's many different definitions of mass applicable to different systems and in different situations. And that has to do with the nature of gravitational energy, which is a topic that deserves a whole presentation on its own, I think. So I'll not say too much about that. But I think some of the interpretations in general relativity have a shared characteristic, namely that they are global in some sense. And in this case, it's global in the sense that it's a quantity defined at a boundary that tells us something about what lies within that boundary. And because it's global, that kind of contradicts our traditional intuitions about mass, something that's local and ascribable to a specific spatial temporal region. So it's extra interesting to really look into this and think about why we call this a mass.
Do you include quasi-local under global here, or is it going to be in a separate?
So quasi-local definitions are definitely interesting, but I have not taken them into account explicitly here.
But you're just essentially local and global.
Yeah. So I want to focus on two particular aspects of this interpretation. The first one is kind of a definition of what mass is within this interpretation. Within the interpretation, mass is understood as a measure of space-time deviating from flatness. It's a symmetrical notion, as I will show, and therefore a geometrical notion. And I think one of the conceptual grounding of this idea of mass is that it's a conserved quantity. And as such, well, in this case, it's also the mass of an isolated system, which means we neglect external influence, we neglect any expansion of the space-time, we neglect the cosmological constant, and we do that by incorporating asymptotically flat boundary conditions, which are very common in black hole physics. So to kind of illustrate the importance of these two aspects, I will focus on this particular definition, the Arnowitt Misner mass. This was introduced in the late 50s, beginning of the 60s in the previous century, and it's formulated within the Hamiltonian formulation of general relativity. And this formulation is based on the idea that you can split space-time into 3 spatial dimensions and 1 time dimension. And you do that by, among other things, splitting up the space-time metric into an induced metric, which describes a spatial slice. So that's what we see here. This is the entire space-time. And this is the spatial slice with the boundary S. And you get a flow factor, and that describes how the spatial slice evolves over time.
Sorry, what's the boundary thing? Maybe I think I missed it on the previous slide.
Well, the boundary is S.
But why is there a boundary in this?
Well, you can see the boundary as lying at infinity, which is hard to depict, but yeah. So if you use this formalism, then the total gravitational Hamiltonian for compact vacuum spacetimes is given by this equation. And then if you choose your slicing well, you pick your gauge, and then you can freely set n to 1 and a to 0. And you then end up with an equation that we say is the energy of this system. So this is an integral over the deviation of the induced metric at spatial infinity. So to really appreciate that this equation is actually an energy, I think we should look a little bit more into what this arrow is doing here. So because we've set up the space-time in a particular type of way, namely we require asymptotic flatness and the metric to be asymptotically Lorentzian, we have an asymptotic time translation at the boundary. This means that Newton's theorem applies, and the corresponding conserved current is called an energy. So I think this is what provides the conceptual grounding for calling this now just a mass, but or an energy. But what we kind of use this energy as the first position in a 4-factor, and then the length of this 4-factor gives us a mass. So we cheat a little bit and choose the rest frame, then this equation is giving us a mass. And what we see here is that it's a metrical notion of mass, like I said. So it's a geometrical notion of mass. So let's check what we get if we fill in the Schwarzschild spacetime metric in this equation. Well, like I introduced before, this is the metric of this spacetime. Let's see if it satisfies the criteria for the ADM equation to apply. Not spatially infinitely extended, and we can see it as an isolated system because it requires the right conditions for asymptotic flatness, and it's a system that's conserved in energy, static space-time. So the first step is then to choose a spatial slice to coincide with an instant of time. It's very easy in this case because we have static space-time. That gives us this induced metric. And then I hope you'll trust me because I don't want to do all the calculations here. But if you fill this in the equation that I showed you before, then what you end up with is that the ADM mass is this M parameter of the metric. So this is often seen as a confirmation that this ADM equation really gives us a mass. So let me summarize what I've said so far about this global mass interpretation, in particular the ADM mass. It's a global notion. It's formulated within the 3+1 formulation of general relativity. It applies to only a limited set of general relativistic spacetimes. It's for isolated systems specifically. We neglect external influence, expansion of the spacetime. Energy is conserved. Its value is given by the Minkowski norm of the 4-factor, whose first component is the total energy. And this total energy is the sum of both the gravitational and the matter energy. It's a geometrical notion, which is going to be important for the next part of my presentation. And something that I've not mentioned explicitly, but that I do think is interesting, is that it's necessarily a positive quantity that's proven by positive mass theorems.
Wait, if you put a negative m in Schwarzschild,
Yeah.
what does this fellow give? Does it give a negative mass or does it still?
What the equation gives?
Yeah,
Um,
I take Schwarzschild metric, but that m,
yeah,
which we normally think is positive, I simply put a negative value.
yeah, well, you
What
can.
will ADM give me?
Uh, I don't know, actually.
Okay, because you say there's a positive mass theorems.
Yeah, so I think it was just not give this, like, maybe,
Okay.
yeah.
It'll
Yeah.
give some other positive number.
No, I can't tell you in detail. I'll have to think about it now.
So it's actually a naked singularity
Yeah.
and it
so-
breaks global hyperbolicity. So you
But-
can't have a 3+1 split of that spacetime.
Or you can't even do the 3
Yeah,
plus.
you can
one.
write down a Hamiltonian for that.
But it's still a static
It
metric.
is static, but it's not globally hyperbolic. So you can't
That
write.
was not one of the assumptions.
Yeah, in the 3+1 formulation, you require the spacetimes. So when she says a limited set of spacetimes, it also assumes that you have to be globally hyperbolic.
Neil says that the theorems also by
Right,
energy conditions, and so if you had a negative mass, it would violate the energy conditions because and the theorems require the energy condition.
Okay.
Okay. If there are no other questions, then I'll turn to the next part. So if we take this global mass interpretation as a valid interpretation for the mass of the Schwarzschild spacetime, then what does that imply for the ontological status of spacetime and matter when we consider it alongside the other interpretations that we've introduced? Well, first, I think it's important to check if this ADMS valid also as a matter criterion.
So before you go to ontological, so let me ask you a naive question, but people have been discussing it, debating it for centuries. That is, you said dichotomy between matter and space-time.
Mhm.
Are they independent of each other? Can one exist without other?
Well, that's a very big question, which we are thinking about. And kind of what we think in our project is no. That's a short answer.
So they are dependent on each other.
They are in some sense dependent on each other. For example, where do you put the metric? That's a question that people
So there
ask.
cannot be any empty space-time without any matter.
Well, it depends on which approach you take to it. I guess what I will be arguing is that in the case of the ADMS, it's like you have a vacuum space-time that has a mass, which is therefore in some sense matter. So this is exactly the kind of questions that we're trying to answer in this project by focusing on different case studies. For example, inflation is another case study that we look at, or scalar theories in general. Antonio Pereiro is looking at that, and he is also looking at, well, if you start out with these categories, how do you kind of decide in which category every entity goes? Is that dependent on the other entity that you're then looking at? So yeah, it's I think also a case dependent thing and definitely a question.
Okay.
So back to the ADMS, can we see this as a criteria for something to be matter? Well, it fails to satisfy the strict criteria of being representable by a stress energy tensor. It also fails the criteria of being ascribable to each point in space-time. But it does satisfy the criterion of being ascribable to a particular space-time volume. So in the context of the Schwarzschild metric, I would say there's a weak sense in which the Schwarzschild spacetime can be considered matter within this global interpretation. So let's take this and use it to look at the ontological status of spacetime and matter. And I think it's one way of approaching this is by looking at the debate between relationalists and substantialists. And I'll focus in introducing this interpretation mainly on what they think is the fundamental substance and fundamentality relations between these substances. And I take these definitions from a paper by Dennis Lane-Cool from 2018. So the relativists, they think that matter is the only kind of fundamental substance. Space and time are just abstractions of or derived from material bodies. Then substantivalism, that holds on to the idea that space-time is a substance in its own right, and it's more fundamental than matter. So matter can still be a substance, but they believe that space-time is the more fundamental substance. Then there's supersubstantivalism, which I think is a third position that's a bit less well known than the other two. And this holds on to the idea that space-time is the only kind of fundamental substance, and that matter is either identified with or constructed out of space-time. So if we focus mainly on supersubstantivalism, then we see that the global interpretation, just a recap, it's a geometrical definition, it's a mass of a space-time itself. And it's the global space-time structure that makes black holes space-time material, as I've argued. So this really suggests a supersubstantivalist position.
Can I ask you a question about that? Does that mean that if you were given a space-time, then there would be a single solution for where you associate matter with that space-time?
I'm not sure I understand your question.
Well, I mean,
Isn't that in a sense the Einstein equation?
I guess, and the supersubstantivalism, can't even say it. But if space-time is the only fundamental substance, if you just gave me a space-time,
Yeah.
I wouldn't need to know where the matter was, but I could derive where all the matter had to be. They're a unique solution, is what I'm saying.
So I think I'm not used to thinking about supersubstantivalism in the way that you're thinking about it right now, but I'm gonna try to give a different answer that maybe hopefully will still help you understand it. So one way, one kind of branch of supersubstantivalists is the Wheeler approach. So like kind of having these knots in space-time that don't have properties like particles also have, such as a mass. So in that case, it's really only like a topological configuration of space-time itself that gives a matter like property. So that's, I think, what I mean when I say supersubstantivalism, the idea that matter is not in itself a substance, but it's made out of space-time substance or identified with space-time. Is that somehow helping?
What do you mean by space-time here? Does it have to be 4 dimensions? Because, for example, if you do 5-dimensional space-time and impose some condition, you can Kaluza-Klein reduce to have, gauge fields and dilaton and scalar fields inside the 4-dimensional space-time that is after Kaluza-Klein reduced from 5 dimensions.
Yeah, I think that's all super interesting things, and we can definitely learn from that about what we're actually observing. But like, there's many steps in between going to higher dimensions and letting that, checking what effect it has on our 4-dimensional world. So in general, when I'm saying space-time, I'm thinking about 3 + 1, just because that's.
But do you just mean curvature? Because you're asking, do you just mean the curvature? Do you just mean the metric, or do you mean an action in that space-time, or maybe that's part of it?
Yeah, I just wanted to know whether the space-time just means that.
Maybe it means curvature.
It means differential manifold with either a connection
Okay.
or.
Yeah.
Or
Good, yeah, so no action.
Okay.
Yeah.
No action.
I think that's what she's saying.
Okay.
I think what you're thinking of is you start with some higher dimensional action on top of a manifold. Then you dimensionally reduce, and that will give you some gauge fields or scalar fields or whatever. But if you, right, you see what I mean?
Yeah.
Well, you need to put the gauge symmetry somewhere, right? So your matter has SC3 plus SC2 plus E1. Like, are we ignoring it, or are we saying that's also coming from the geometry somewhere?
as you're presenting it right now, it's something that matter has symmetries.
Right. I'm just saying matter is not fundamental.
Well, in the supersymmetric difference position.
Yeah, exactly.
But yeah, you can think about does the space time have its symmetries or does the matter have?
So putting those symmetries in space time as well.
Well, I'm not putting them.
Well, I
anywhere.
mean, the super stand. That's-
Yeah, they would I think say yes. Everything is in the end fundamentally space time.
Maybe I can echo Chef's question back on this point. So when it says constructed out of, is it a uniquely determined construction, or is there like, are they okay with that kind of undetermination of what you get out at the time?
I don't know. Yeah, that's I think the most honest answer I can give.
Yeah, because you can imagine like it will reduce to, and you know, space-time is more fundamental, but there's an emergence property that's not uniquely determined.
Yeah, but I guess for the argument itself, or the like what the most fundamental substance is, if some, yeah, I'm not sure the underdetermination. Yeah, so that's like an argument against that. Yeah.
So this space-time is the most fundamental without considering any physics or anything. So just conceptual things. So you are considering it's a background, right? Space-time is a background, or is it something? And when you say time, time usually has many interpretations. One is order. So what is the order if there is nothing else? Order between what?
Well, I think that's kind of, if you see space-time as the only fundamental substance, then it's kind of in there, in the definition of what you think as space-time.
I think I could echo on this idea. This idea might be related to what Wheeler's idea of charge without charge.
That's what I was trying to refer to.
Yeah,
Yes,
that
yeah.
if you look at the Reissner-Nordstrom solution of Einstein's equations, there is no electromagnetic charged matter under the electromagnetism anywhere in space-time. Okay? And if you take a spatial cross-section, you can hide it. You can think about it as one side has positive charge of the wormhole, the other side of the wormhole is negative charge. So you can get charge without like charged matter.
Okay, I think we should let you continue.
Yes, yeah. If you have any questions, please ask me at the end of the break. Yeah. So yeah, just to recap, I think that the global interpretation suggests a supersubstantialist position towards the ontological status of space-time matter. So let's check what the other interpretations imply on this status. So I'll just quickly go through them. The dimensional analyst interpretation, like I said, it's quite a thin interpretation. I think it's pretty hard to say anything about what that interpretation suggests. But what is apparent from looking at the other ones is that there's a clear contradiction there. So if you focus on supersubstantialism, then basically only the Newtonian trickle-down interpretation and the global interpretation support that view of space-time and matter. And the other ones don't. So they either support a dualistic substantialism stance towards space-time and matter, or a relationalism. Which is interesting because we started out with the idea that all of these interpretations capture some essential aspect of what it means for Schwarzschild space-time to have mass, or how to interpret this M parameter as a mass. So what should we do with this contradiction of all these interpretations? Well, one way to respond to it is to actually the distinction between space-time and matter. We should let that break down. So we can either, in the context of a Schwarzschild space-time, reject that these are separate concepts. And this is also what the ADMS supports. Space-time is matter in the case of the Schwarzschild space-time. Or we can throw away the categories altogether and say, well, actually, they don't bring us anything. They're not good conceptual tools to talk about what's happening in this context. So, recap. I've said that the global mass is a geometrical notion of mass. It's conceptually grounded in the idea of energy conservation. And a specific instance of global mass is the ADM mass, and that can serve as a matter criterion for the Schwarzschild spacetime. And this global mass interpretation implies the breakdown of the spacetime matter distinction in two ways. Namely, it says that the Schwarzschild spacetime itself can also be seen as matter. And it also contradicts other interpretations of the Schwarzschild mass on the ontological status of spacetime with respect to matter. So I went through it a little bit quickly. So if there's any questions, then let me know. Okay.
I think we probably have many questions.
Great.
So,
I hope I can answer some of them at least.
if folks on Zoom have questions, feel free to raise your hand or type them in the chat and I can call on you.
So you're trying to answer a very difficult question, right? Like Leslie was also mentioning, what is the energy in the gravitational field, etc. That's the overall game, a good overall problem. So when you look at the super substantialist, whatever that thing, that position, so that might work for vacuum spacetimes, where you can say there's no literal gas anywhere. But when you go away from vacuum, when you go to non-vacuum spacetimes, that position becomes slightly untenable, right? You can actually identify some volume where you can actually see that there are gas molecules or whatever. So, so how does that change your picture once you move away from Schwarzschild?
So you say, why would it, you're basically implying that it would make a difference? Could you repeat why?
Right. So let me just, you're thinking about Schwarzschild black holes. If we think about stars instead of black holes, they still curve space, etc. They have all the fundamental, they're curved space, right? But with a star, you have matter actually, some kind of perfect fluid, etc. So you can say there is also curved spacetime. There's some energy somehow that's stored in the curvature of spacetime. And there's also energy stored in the gas itself, rest mass energy, etc. So I'm trying to understand how, if you move from the example of a Schwarzschild black hole to the next nearest thing, will you immediately break super substantialism? Will your position shift to substantialist?
Yeah, that's a good question. So I think how I see the ADM interpretation or the ADM as supporting supersubstantialism is by the fact that if you look at the equation, then there's only a metrical thing in there. So it's really made up of the curvature of space-time. So it also describes the total mass of the system. So I think it still holds up. It doesn't really tell you what kind of mass, if you want to ascribe it to gravitational energy or matter and type of energy. It doesn't say anything about that. So I think you can still say, well, this global interpretation supports a supersubstantialist.
If you say that the spacetime is the most fundamental third option and matter is still built out of it, so which means that there is only spacetime. Matter is simply another manifestation of spacetime, right?
Yes.
So so whatever you see as better, still spacetime, you define it.
Somebody asked a question, not answered.
I think it was a elaboration.
Okay, well, there could be one potential worry about this whole discussion about ADM mass because it doesn't constrain the motion in the bulk of space-time. For example, you can have space-times that have the same ADS mass, or even I can have every single, let's say you have spatial infinity, which is where ADM mass is defined, and you can have ADM type energy and ADM momentum. You have two drastically different asymptotically flat spacetimes that have the same ADM mass. How would you account for that?
In what context? Because I think, well, I can have the same as a table.
So how would you, if you say that ADM mass or this type of thing corresponds to matter, then how does your notion of matter tell which matter is which?
It's not the point though of what she's trying to do, right? I don't think. Doesn't seem, yeah, I think what you're saying is correct.
Yeah, I think you can't. Basically, the idea of this global interpretation is that you are not able to say what exactly is at a certain location, for example, within that space-time. It's a definition that lives at a boundary. It tells you something about what's happening inside there, but in a limited way.
Oh, okay.
Yeah.
Thank you.
I hope that answers.
Awesome. Okay, so this is kind of building on Brynon's question, but in a different direction. So this question was about like these kinds of case studies put pressure on our usual interpretation. And so that's kind of the point of going to these strange vacuum cases, because then you're saying, look, in these cases, we like don't have what we usually think of as giving rise to mass. And so it puts pressure on your usual intuitions. But I have the flip side question. So I'm kind of worried about the idea of using such idealized situations to draw metaphysical conclusions. So how do you think about this? So like we're moving to this really idealized notion, and I'm fine granting that it puts pressure on our usual interpretations, but I don't necessarily think that then we should take what it tells us as metaphysically real, because it feels like, well, yeah, because you worked in this really idealized situation, you can draw out these kind of strange metaphysical conclusions, but that doesn't mean that we should believe in them because they have these idealizations that were in part of why you got the metaphysical.
Yeah. This is a question that we're also thinking about. One way, I guess, in which we've approached that question so far is by really focusing why would someone even call this global mass a mass? If you think it's justified to call it a mass because it's based on the idea of energy conservation and similar, for example, as in special relativity. So if you believe that this energy conservation has that metaphysical value, then maybe it also counts in this case. But then still, of course, the fact that it only applies to very specific spacetimes, idealized spacetimes, with asymmetry or it's a vacuum, indeed. Then I think it's a very good question to ask, what can we learn from those type of spacetimes and the mass of those type of spacetimes about astronomical black holes. Yeah, people have written papers about that. It's very interesting. We've talked about that before. I do think that, well, physicists now are working with this notion of the ADM mass. For example, they're doing numerical relativity computations, simulations, trying to understand theoretical things like cosmic censorships, but also other systems, how they evolve. So there's definitely some value in looking at this mass, even though it's only for idealized systems. It's only defined for idealized systems. But it's a good question, I think. What exactly is the link there?
I mean, if you had a situation, like I totally buy it that practical utility means we should be considering them. But then the question is, if you were to de-idealize various components of it, do you still retain the same metaphysical conclusions? And I don't know to that kind of approach.
Well, we've talked about it before. The paper has been published by Vergouwen. This is all can't be idealized. That's a big problem. Yeah, so that's one answer to that.
Other questions? Questions on Zoom?
I think I'm kind of missing the key point here. You're working with Schwarzschild, fine. But listening to all of your arguments, it looks to me that I can do this with Newtonian physics. I can just say, I got something. What is the mass as measured at infinity? And of course, I can get a certain mass, which is only one number, doesn't know anything about the details of what's in the middle. Like you said, you and the table may have the same mass as measured at infinity, and yet we know that these are two different physical situations. So in Newtonian physics, we would say, look, there is something called matter density, and it's related to something called Newtonian potential through some Poisson equation. Asymptotically, I can look at what the potential does. I can do some surface integral of that gradient of the potential or whatever, and I can measure a mass at infinity. I'll do this in Newtonian physics. We do it all the time. And it gives me one number of describing what's in the middle. Okay, and you'll have your dimensions of mass. So far, I'm with you. I'm not seeing a difference between this and using the Schwarzschild metric. What's extra here in the Schwarzschild problem? Because now my asymptotic mass cannot tell the difference between a real point mass, M, and Prashant's star, a sphere with a distributed matter density, but still has the same asymptotic M. These are two different situations, and yet, we think they are two different situations, that they are not the same problem. Just because they have the same M at infinity, so what? That, I think the key point somehow I seem to have missed. Sorry, yeah.
Well, I think this will be one approach to trying to understand what mass is, right? That you're describing right now, and what we we're thinking about is that there's many ways of approaching that, and I think the Newtonian way of approaching the mass of a system is different from the way that the global way, the way that people do it in general relativity, because then you also extra things you take into account, like gravitational waves and all these type of things. And in the Newtonian case, you are indeed able to say, okay, well, if I look at this limited region in space-time, then it has this mass. You have a mass energy density, and that's just simply not. It doesn't seem we're not able to do it right now in general relativity.
Why not? Isn't that what Einstein's equation is? Given the local metric, I can do some operations and measure the stress energy tensor or calculate it. That's the same as using Poisson's equation on the potential and.
But she's in vacuum here. Right?
Okay, that's a special case. Okay, but what is the problem? Yeah.
Well, I think in the examples that you were giving, there is you could go in and look at what the matter is. Right?
Yeah.
You're giving examples of a table and a point particle.
And a point particle.
Yeah.
Point particle has only matter at r equal to 0.
Sure, but it's
She has
but it's a
matter
point
at r.
particle that has mass. It's I think she's looking at situations that there is no actual matter. Right?
Is a point particle in Newton different from the Schwarzschild situation? To me, they're the same. Both have an infinite, singular something at r equal to 0 and vacuum everywhere else.
Well, but r equals 0 in Schwarzschild is not
Part of the space-time.
it's an instant of time. It is not a
Yeah.
singularity that is space-like, right?
That's right.
So I think
It's not a point particle, right? It's the end of time.
It's a
It's very different. Yeah.
the other important thing I think is like if you look at the Misner mass, or which is the quasi-local version of one of the quasi-local versions, you can define quasi-local mass, but that will not. I mean, it's not very clear what the interpretation of that is. Whether it's the energy density of the matter is the energy density of the space-time curvature. What? Because as we've discussed, it doesn't have the integration of the energy density with proper volume. So the difference between these two is seen as the gravitational binding energy or quasi-local mass that is in the space-time.
I guess I didn't see all of that.
No,
so,
it's not. But these
yeah.
things are ambiguous. And so the big question is, how do you say what is related to the space-time? What is the pseudo energy momentum tensor of the space-time? And what is associated with the stress tensor of the matter? So that's the overall big question, I think, if I'm sorry for paraphrasing it. And in that context, they want to identify which is which. So again, what is the pseudo energy momentum tensor? This is a old problem, and this is not clear. So I think they're looking at one specific case, which is Schwarzschild. So we know some facts already about Schwarzschild. It's vacuum, there's nothing anywhere. So you can kill off the stress tensor of the matter. So now they're trying to ask, what is the pseudo-energy momentum tensor? How do you interpret that? So let's look at various definitions of mass, one of which is the global definition. And that gives you some understanding of how to interpret like what is inside the space-time. Then presumably in this program, they will look at other spacetimes and draw other conclusions and make some concrete final answer that, okay, this is what we should think about where the energy density is. Is it in the spacetime or the matter, or etc. I mean, that's how I was understanding the framework of your talk. But
Yeah, the last part is definitely interesting. I'm not sure if we're going to do that. Yeah.
Right. Yeah, that's hard, I guess. Yeah. Yeah. But that's it seems like a very interesting goal. Yeah. But I don't know if that kind of,
I don't know if you're only working at infinity.
Right. Yeah.
To me, it's not clear what you're saying. Yeah, that's really what's bothering me.
Yeah, I think it's interesting.
If we were to investigate the whole space-time, and then say, yeah, such and such, look at this, whatever, there's a contradiction, or it makes no sense, or whatever, I'll understand. But the entire discussion was at infinity.
Yeah.
So maybe, so I think what seems to be a problem here as well is that we're trying to kind of compare your interpretation with the global mass interpretation as I did it, but it's quite hard to compare them because it's like you have different language of word and different computations you do, and it's something we also think about in terms of these interpretations. What are the relations between them? We do think they all are referring to the same thing, namely this mass, but in some cases it's clearly in an idealized situation, and in another case it feels more realistic or more resembling to an astronomical black hole. So thinking about what's happened at infinity is maybe not as useful in one interpretation as it is in the other interpretation, and in the global interpretation it's necessary because you can't think about what's locally inside of the space-time.
Okay, I don't see any other questions, so question Sanne again. Thank you.